In the last video, we finished talking about Galilean relativity, which is the relativity of everyday life. Now let's talk about special relativity, which is the relativity that we observe when close to the speed of light. The story of special relativity starts in the 19th century with the four Maxwell's equations of electricity and magnetism. You may find these equations confusing if you haven't studied them, but you're probably familiar with their physical meaning in everyday life. For example, Gauss's law says that opposite electric charges attract and like charges repel. And this equation says that every magnetic north pole comes with a south pole attached, and that there's no such thing as an individual north or south pole. Maxwell's equations turned out to be remarkably successful at describing electricity and magnetism, and they are responsible for our modern electrical technology like microphones, speakers, and radio antennas. However, there is a problem with Maxwell's equations. When we combine all four of the equations together, we get equations for electromagnetic waves, or in other words, light. The equations say that light will travel in a vacuum at a speed denoted by c, which is 300 million meters per second, or 3 times 10 to the 8 meters per second. Now, we know that the speed of sound waves can be measured relative to air particles. And we know that the speed of ocean waves can be measured relative to water particles. But what is the speed of light measured relative to if it can travel in a vacuum? Remember, Galilean relativity tells us that there is no special stationary reference frame, and that all motion is relative to something else. So what are we measuring the speed of light relative to if it can travel in a vacuum, which is just empty space? To get around the problem of the speed of light being defined in a vacuum, physicists tried to propose an invisible fluid called the ether, which would be a special stationary reference frame that light traveled through. However, tests like the Michelson-Morley experiment involving light beams and mirrors showed that the ether didn't exist, leaving physicists once again with the problem of the speed of light being defined in a vacuum. This is where Einstein comes in. Einstein proposed that the speed of light c was the same in all reference frames. Another way of saying this is that Einstein treated the speed of light in a vacuum c as a law of physics. So, in an attempt to build a new theory of relativity, Einstein began by agreeing with Galileo and said that the laws of motion should be the same in all inertial frames of reference. But he expanded this principle to include not just Newton's laws of motion, but all laws of physics, including Maxwell's equations, and he made the speed of light c a law of physics that is agreed upon in all inertial frames. And these are just Einstein's two postulates of special relativity. Postulate number 1 says that the laws of physics are the same in all inertial reference frames. And postulate number 2 says that the speed of light in a vacuum c is equal for all observers in all inertial reference frames. You could also rephrase this by saying that the speed of light in a vacuum c is included as one of the laws of physics. Unfortunately, these postulates are not compatible with Galilean relativity. To see why, we can consider our example of the scientist on the ground, and the car traveling along with speed v to the right, this time with a giant flashlight attached on its roof. In the frame of the car, the driver sees the scientist pass by with a speed v to the left, and the light coming out from the flashlight travels right with the speed of light c. But in the frame of reference of the scientist, since the car is traveling right with speed v, the light coming out of the flashlight would appear to have the speed of light c plus the speed of the car v. But this violates the new postulate that the speed of light is a law of physics that's constant in all inertial frames, which includes both the car and the physicist. So unfortunately, the information on the screen in front of you contradicts itself and is not consistent. But there is a way we can create a new theory of relativity where the speed of light in a vacuum is a law of physics. And that's by taking time, space, and mass and changing them from things that everyone agrees on to things that everyone can disagree on. In the theory of special relativity, time, space, and mass become relative and depend on the observer's reference frame, just like velocity, momentum, and kinetic energy. To understand why time, space, and mass become relative, Let's consider the example of a train passing by a station at a constant speed v. The speed v is measured relative to the platform on the ground where a scientist is standing. Now let's see how a beam of light behaves on the train. We'll shine a beam of light across one of the train cars in a direction perpendicular to the train's travel direction. The beam of light will be reflected by a mirror back to where it originally started. We can use the amount of time the light beam takes to travel this distance as a kind of clock. Except instead of ticking once per second, the clock will tick once every time the beam of light crosses the train car in one direction. Let's start with the train's frame of reference. A passenger on the train will see the platform outside pass by as the beam of light travels back and forth. If the width of the train car is given by the distance d, and the light beam takes a time delta t to cross the train car in one direction, then delta t would be equal to the width of the train car d divided by the speed of the light beam c. Now let's consider the frame of reference of the platform with the scientist on it. The scientist sees the platform standing still as the train passes by. Notice how the beam of light now travels in a triangle shape because of the train's motion. Remember that time is now relative and depends on the reference frame. So we will now call the time it takes for the light beam to cross the train in one direction a new symbol, delta t tilde, where tilde is just the name of this wavy symbol above the t. Again, the width of the train car is d. The distance that the train has traveled in this time is just the train's velocity v times delta t tilde. And the distance that the beam of light has traveled is the speed of light c times delta t tilde. Now we have three distances here that make up a right-angled triangle, so we can use Pythagoras' theorem to relate these three sides. The sum of the squares of the shorter side lengths equals the square of the longest side length. Now we will divide all terms in the equation by c squared. Then we use subtraction to bring this term to the other side of the equal sign. Then we replace d over c with delta t, which is the time that the light beam took to travel across the train car in the reference frame of the train car. Now, if we divide both sides of the equation by this term and take the square root of both sides, we get this. We find that the travel time of light in the frame of the platform, delta t tilde, equals the travel time of the light beam in the frame of the train, delta t, times this factor, which we often write as the Greek letter gamma with a subscript v. This factor is called the Lorentz factor, and it is always greater than or equal to the number 1. This tells us that delta t tilde is actually greater than delta t. In other words, the travel time for the light beam in each reference frame is not equal. So we've discovered this Lorentz factor causes time to be a relative quantity. When we measure the time between clock ticks for a moving clock and measure the time between clock ticks for a stationary clock, we find that the time between clock ticks for the moving clock is actually larger. This effect is called time dilation, and it basically means that a moving clock will tick more slowly than a stationary clock. There is a similar effect on space called length contraction, where rods that are moving appear to have a shorter length than the same rods when they are standing still. However, length contraction only happens in the direction of motion. In the direction perpendicular to the motion, no length contraction happens, and identical rods will be measured to have the same length. There is a similar effect on mass where moving masses are measured to be larger. So we now see that time, space, and mass are relative quantities that depend on the reference frame that we're in. But this definitely doesn't match up with our everyday experiences, so how can it be true? Well, the everyday speeds of cars, trains, and planes are much smaller than the speed of light c, and we see in the Lorentz factor formula that if the speed of the reference frame v is much smaller than the speed of light c, then v squared over c squared is basically 0, meaning that the Lorentz factor is basically equal to 1. This means that all inertial reference frames universally agree on time, space, and mass. So the effects of special relativity are not apparent at everyday speeds. We only notice the effects of special relativity at high speeds close to the speed of light. At high speeds, like the speeds of faraway galaxies or the speeds of subatomic particles, special relativity needs to be taken into account in order to understand the physics properly. As an example, physicists have confirmed that time dilation is a real physical effect by observing its impact on the lifetime of muons. Muons are subatomic particles created in the Earth's atmosphere by cosmic rays from outer space. Like the electron, the muon is a negatively charged subatomic particle. However, unlike electrons, muons are unstable and decay in about 2.2 microseconds on average. Without the effects of special relativity, a muon traveling at 0.995 times the speed of light travels about 650 meters on average before it decays. This is not enough time for a muon to reach the Earth's surface from the atmosphere where it was created. However, if we take the velocity of 0.995 times the speed of light, the Lorentz factor from special relativity ends up being about 10. This means that, taking the effects of special relativity and time dilation into account, a traveling muon will live for 10 times longer its expected lifetime, as observed from the stationary Earth, and the muon will travel about 6.5 kilometers on average before decaying, which can be enough to reach the Earth's surface from the atmosphere. If the muon travels even faster, this means the time dilation effect will be even greater, meaning the muon can travel farther distances, even going underground, before it decays. The fact that we see muons reaching Earth's surface is real physical evidence that special relativity is correct. If special relativity was wrong, muons would decay before they ever reached the Earth's surface. So, to sum up special relativity, the two postulates are that all laws of physics are the same in all inertial reference frames. And we also have to remember that the speed of light in a vacuum C is also a law of physics that is the same in all inertial reference frames. This means that all inertial reference frames will agree on Newton's laws, Maxwell's equations, and the speed of light. But different inertial reference frames will disagree on time, space, and mass, as well as velocity, momentum, and kinetic energy. So we've covered Galilean relativity and special relativity. In the next video, we'll focus on the final theory of relativity, general relativity, which is a theory of gravity.